Hi there. In this video, I'm going to do just a very quick summary of the things in chapters 6 and 7 that we're not covering. Although at the very end of this section, I do cover one topic that's pretty straightforward that is part of the AP curriculum. So chapter 6 is about different kinds of applications of integrals, and only a few are explicitly covered on the AP. But you will see some of these in future math or science classes, so I want to give you just a quick sense of what's going on. The AP wants you to understand how to use integrals in a general way, for example, the net change theorem, but it's not expecting you to know all these individual formulas, but they are kind of interesting. So 6.3 is a different way of finding volumes called the method of cylindrical shells. So we've talked about the disk and washer methods. There's another way of slicing up round things in a different kind of fashion that can also help you find volumes. Section 6.4 is about arc length. So arc length is asking, like, literally how long is some function's graph. So if I have y equals f of x and the graph looks like this, and I want to know what's the actual length of the curve from A to B, if I were actually a little bug moving along that graph, what is the distance traveled? And the way we would find this, which should sound familiar, we estimate it and then take a limit, which turns into an integral. Right? Sort of the trick here is you estimate this curve by drawing a bunch of line segments and figuring out a formula for the total distance of those line segments. Then you run a limit and it turns into an integral. Section 6.5 is surface area of a surface of revolution. If we spin something around, like we saw in some volume problems, maybe we want to know, well, actually, how much area is there on the side of this thing? So, for example, if we have, some curve like that, and we imagine spinning it around, to get something kind of round like this, right? What's the area on the outside of that thing? There's a formula based upon a limit process that gets that for us. Section 6.6 is about work. In physics, you may have learned that work is force times distance, but the problem is force isn't always constant. If I move closer to a magnet, the magnetic force is stronger. If I move farther away from a massive object, the gravitational force is weaker. So if force is changing, we can't just say, oh, take the value of force and multiply it by distance. But there's a formula with integrals that does this. Section 6.7 is about moments, centers of gravity, and centroids. So if we have some irregularly shaped figure, there is, in theory, a point that is the center of gravity, right? There's some point that's, quote unquote, the center, even though this thing does not have perfect symmetry. But in theory, if we imagine this from the side, there is a point where the whole thing would balance on that point. So you imagined it like a piece of paper on the tip of a pencil. If you have the pencil tip in just the perfect spot, the whole thing will balance. There's a way of finding that location using an integral, assuming you have formulas that describe the edges. More with force and fluid pressure. So just another thing with force and how integrals relate to it. Section 6.9 is about hyperbolic functions and hanging cables. It introduces two functions called hyperbolic sine and hyperbolic cosine. And these are not trigonometric, but if you were to graph these functions or take their derivatives and see how the derivatives relate to each other, you would notice that they behave in a way that is somewhat reminiscent of sine and cosine. Hyperbolic cosine is an interesting one. The graph is what's called a catenary, C-A-T-E, I believe, catenary. And if we have, for example, like a hanging chain or cable or something like that, so, if we hold up the edges of the cable and then it just kind of droops like that, the shape would be something, some transformed version of that formula. That shape is called a catenary. When you take into account the tension within the cable and the force of gravity, the natural shape it would take when you let it droop is called a catenary. It's not a parabola. So that's chapter 6. And some of this you might see in a future math class. A few of these are covered on the BC curriculum. Some of them you might see in a college second semester calculus class that delves a little bit deeper into applications of integrals. Some of them you might just see in a physics or engineering class, because a lot of these you don't really need to know a lot of concept behind them. If someone could just say, all right, if you need to figure out work, you do this integral. And as long as you know how to do integrals and remember that formula, you're good to go. So maybe the whole explanation will not be taught to you, but it will be assumed that you can apply the formula. Now, chapter 7 is about techniques of integrals. You know how to take integrals of very simple functions. You know how to do U substitution, and that's about it, right? Maybe you can cleverly rewrite something, but not every function can be done that way. So some examples would be this integral, this integral, this integral. None of them could be done with U substitution, but there are some clever techniques that you could use. So there's a technique called integration by parts, which is essentially integral's attempt at a product rule, but it's not as powerful. Here you could use what's called the method of partial fractions. And here you could use a special kind of substitution called a trigonometric substitution. So again, some of this you would see in BC if you're taking that next year. Some of this you would almost certainly see in a second semester college calculus class. Because there is a, you might need to do integrals a little more exotic than what you've seen before. Historically, this has been really important, that computers that could do integrals are a relatively new invention. So engineers and scientists would have to know a lot of techniques if they wanted to do the particular integral that solved a problem for them. Luckily, that's not as important to us. So a lot of chapter 7 is just rolling out different kinds of tricks and rules for actually doing certain kinds of integral problems that appear very hard. Now, the one section we are going to talk about where you need to understand it is section 7.7, which is about numerical integration. And really, it just rolls out one new thing that should be pretty obvious. So part of this is a repetition. So let's suppose I have a function f, and I'm just giving you this table of values. So using a left endpoint approximation, estimate the definite integral from 1 to 10. So if you wanted to, you could draw a graph, or we could just sort of imagine there would be 1, 2, 3, 4 intervals. So for each interval, we could think, what is our function value? And what is our width? What's our change in x? So our first interval goes from 1 to 4. It's 3 units wide. And if we're doing a left endpoint approximation, so I'm not going to draw the full graph here, but just to get us starting. Because the whole point here is you do not need a graph to do this. You just need to understand the relationships. But here's x equals 1. Here's x equals 4. The height at 1 is 3. The height at 4 is 1. So when I say a left endpoint approximation, that is like drawing a rectangle. Here's the base of our rectangle. How tall is it at the left-hand side? And at the left-hand side, that's f of 1. So f of 1 is equal to 3. And then we would do this for the 4 different intervals. Function value times the change in x. So the function value for the next one goes from 4 to 5, so it's just 1 unit wide. Function value at the left is 1. Next one, function value times the change in x. Well, our third interval goes from 5 to 7, so it's 2 units wide, and at that left endpoint, f of 5 is equal to 2. And then finally, last one, like we're computing the area of a rectangle, the width from 7 to 10 is 3, and the function value at 7 is 0. This kind of problem shows up on the AP every so often, and you would be fine to just leave your answer like this. Leaving your answer in this form is both acceptable according to the rules and actually is a nice demonstration of where your answer came from. If you're very clearly writing something times something plus something times something plus something times something plus something times something, it's clear you're doing a Riemann sum. You're adding together function value times width plus function value times width, etc. Obviously, we could compute this. It's 9 plus 1 plus 4, which is 14. So this you've seen before. Maybe you never saw an example where the intervals were not all the same width, but they don't have to be. It's usually easier if they're all the same width, but that's not required. Now, there are other ways we can do this. What if I gave you this same data and asked you to use a trapezoidal approximation? So here I'll draw the picture just so you can visualize what's happening. And you don't necessarily have to copy all this if you're taking notes along with me. So 1, 4, 5, 7, 10, roughly like so. 1, 2, 3, negative 1. So we only know a handful of points on this graph. F of 1 is 3, f of 4 is 1, f of 5 is 2, f of 7 is 0, and f of 10 is negative 1. So we would just have to imagine what this entire graph looks like, right? So maybe, so I'm going to draw something and then erase it. Maybe our graph looks something like so. And what we could do to estimate the corresponding area is to draw a series of trapezoids by essentially thinking, oh, maybe this graph kind of follows some straight line segments. Obviously, it's not perfect, but some reasonable estimate of what the graph is doing would be just to follow line segments between the points we happen to know. So I'm going to erase all of this, and we'll go back to just drawing those. So we can think, all right, the area under the curve for this first region, we could think of in terms of this trapezoid that I'm drawing in red. And let me just point out, area of a trapezoid, depending upon how you look at it, it's either base times average height or height times average base. It's not a rectangle, so we don't have that opposite sides are always the same length. But here, for example, for this first one, it's 3 units wide. The height on the left is 3. The height on the right is 1. So our area for this first one, we could think, all right, it's average height, 3 plus 1 over 2, times how wide that base is. Plus, now we could imagine another trapezoid like so in green. That's 1 unit wide, and the average of its two heights is 1 plus 2 over 2. I'm actually writing this out to show my calculation. Remember, if this were an AP problem, you don't have to fully simplify. Presenting your answer in a way that makes it perfectly clear where it came from is a great idea. What's our next one here? It's 2 units wide, and the heights were 2 and 0. So here this quote-unquote trapezoid actually looks like a triangle after we graph it. So 2 units wide, and the average of the two function values is 2 plus 0 over 2. And our last one here goes below, and we're not doing pure area. We are estimating an integral, so negatives stay in there. So this last one is 3 units wide, and the average of our two function values is 1 plus negative 1 over 2. So this would be our trapezoidal approximation. Basically, instead of doing left endpoint or right endpoint, we average them. Average the endpoints times the width. Average the height of the endpoints times the width. Average the height of the endpoints times the width. This is actually the reason. Trapezoidal approximation is the same as just the average of left and right endpoint methods. And usually it's more accurate than either one. So I'm just going to leave it in this form. Leaving it in this form makes it perfectly clear where your answer came from. So this I want you to know. If you're asked to do a trapezoidal approximation, you think, oh, instead of using rectangles, I'm using trapezoids. And instead of doing base times height, I'm averaging height on the left end with height on the right end. That's the only issue. Now, one other thing that I want you to be aware of is this method called Simpson's rule, which is even more accurate. And this was a very useful method back before people had computers and calculators to estimate integrals. And the trick for this is if you have an even number of congruent subintervals, you can actually approximate the graph not with rectangles or trapezoids, but portions of parabolas. So sort of the trick is, so here's the idea. Suppose I have 1, 2, 3, 4, 5, 6, 7, 8, 9 points like so. What you can do is 3 at a time. There is, in theory, a unique parabola that goes through these 3 points. Then we take another 3. There's a unique parabola that goes through these 3 points. And then there's a unique parabola that goes through these 3 points. And a unique parabola that goes through these 3 points. And in theory, you could estimate an area by saying, all right, I'll take the area under this pink parabola plus the area under this green parabola plus the area underneath this orange parabola plus the area underneath this blue parabola. And this will often be very accurate because we're approximating with curves rather than with horizontal lines or even slanted lines. In practice, it's not obvious at all, but there is a formula that is the result of doing this Simpson's rule thing with parabolas. So this is something I learned when I was in high school. It's not part of the curriculum anymore, but it is interesting to note that there is a formula that gives you a very good estimate of integrals if you don't actually know how to do it using the fundamental theorem of calculus. And this is something you'll see maybe in a future math class, there are formulas that estimate how close these will be. So the idea is you can actually apply different rules to say, so for example, suppose you're trying to figure out the definite integral from 0 to pi of sine squared theta d theta. And you need an answer that's, say, within, what is this, 1/100,000th of the correct answer. There are some formulas that basically say, all right, if you tell me a little bit about how wide your interval is, and you tell me how accurate you want your answer, and there's a little bit that you sort of factor in how exotic is this function. Based upon that, the formula will basically spit out how many intervals you need. And it might say, for example, oh, if you use, and I'm just making up a number, but maybe it'll say like, if you use 40 intervals, then your answer will have the desired accuracy. There's basically a formula that will churn out how many intervals you need if you want a certain amount of accuracy. And a lot of those formulas are built into the calculator. When the calculator, quote unquote, does an integral, it's really just estimating using trapezoids or rectangles. But it's been programmed in how many it needs. So the calculator has programmed in, oh, if I use 150 rectangles, then the answer will be within 1/1,000,000th of the true answer. So that's what it shows you. It doesn't actually do fundamental theorem of calculus. It just gives a really, really accurate Riemann sum approximation. And there are all kinds of formulas that you could learn if you're curious. They are in your book. That give you a sense of how to do this. But all that's coming out of section 7.7 that I want you to be aware of is this notion of a trapezoidal approximation, which is pretty obvious once you understand what it means. All right, that is it for this section and these 2 chapters, right? Like we just did about a dozen sections in one video.